Welcome back, physics fans. Here we go on the curved displacement time graph, one that's just talking a little bit beyond what this chapter is about, a constant velocity. So this really isn't constant velocity because during this section right here, there's no straight line there. It's curved. So that is not constant velocity. Everywhere else is constant velocity, but let's continue on and try to learn here. In the graph to the right, what is the average velocities during these times from 0 to 1? It would be a rise of 4 over a distance of 1. It's pretty simple at that point. Hopefully you got 4 over 1, and this would be 4 meters per second. And this, in my sheet here, will be east, because I need a direction. And this graph is saying that it's the displacement east. Number from 1 to 2, it's the same slope. So this will be 4 meters per second east. From 3 to 4, this is going backwards 1 and over 1 second. So this will be 1 meters per second west. It's rise over run. So it goes down 1 over 1. So this is negative over positive 1. That's why I have 1 west. From 5 to 6, okay, it's up 2. Up 2 in 1 second. Okay, so that's going to be 2 meters per second east. Now from 12 to 13, during this straight portion here, it goes down 3. So this is going to be 3 meters per second west. If it was a scalar one, if I had asked you speeds, it would have been 4, 4, negative 1, 2, and 2. Those would have been the speeds. For F, 13 to 14, it's a slope of, that's an interesting one. Is this exactly in a half? It's tough to say, but let's take the longer version of this, and this goes all the way from 13 to 15 over 2 seconds, so that slope for that last 2 seconds is the same as the slope from 13 to 14 and 14 to 15. That's a fall of 3 over a run of 2. 3 over 2 is 1.5. And yours would be negative 1.5. And on this vector one here, this will be just west. Negative and negative 1.5. Now from 1 to 5 seconds, again, it is the average velocity is 5 seconds over 8 over 5, sorry. Nope, it's from 1 to 5. 1 to 5. 1 to 5. From there to there. So it rises 4 over 4. This would be a nice, beautiful 1 meter per second east. From 4 to 12, starting there and going over to 12, the average velocity, we're right back where we began. We're at 6 when we started and 6 when we ended. So this is going to be 0. 5 to 12. I'm just going to start erasing some of these lines that I put in here so they're not distracting you and me. So 5 is here. And 5 to 11, sorry. 5 to 11. 11 is, are they trying to say it's there? Okay, it looks like it's an eyeball one where we're not going to have it precise. Or is it crossing exactly at that point? We'd have to zoom in at this point. Well, let's just predict that it is exactly at 11. Might not be the best. But that goes down 3 over a run of 6. So rises 3 over 6. So 0.5 meters per second, and that's east. 0 to 11. 0 to 11, that's going to be a rise of 11 over 11, and it is a straight line. Let's just draw that line. I just want to see it. Try to snap it in. Yeah, it definitely goes through every one of those little points there. It's pretty close. So I'm just going to undo that now. We'll get it out of there. We don't need to see it. But that's the final minus initial line, and we get 1 meter per second east, and 7 to 12. Ouch! Where are we here? And over to 12, we are there. So at this point, I don't know, let's just zoom in here. Let's go to 300%. And if you have it on a piece of paper and you want to zoom in, just get your eyes closer to the paper. Yeah, that's an interesting one. That is 7. So where is that? And then how far does that fall? Well, that's definitely falls 1, 2, 3, 4, and maybe 0.8, 4.8 over a run of 5. Okay, there is going to be some error in that. So it goes down 4.8 over 5 seconds. So 4.8 divided by 5, roughly 0.96, 0.96 meters per second west. But this is just reading values off of a graph. So I would accept a little bit of a range of error. I would probably accept anything from 1 down to about maybe 0.9, maybe 0.92 or something like that. I'd have to accept a range there because I'm not telling you exactly what that value is at 7. You're just having a graph that's given to you, and you guys have to estimate. It's more than a half. It's probably a little bit more than 3/4, but you can't do more than one sig fig of answer there. So 0.8, 0.9, 0.7. Doubt it if you can get even to that. And 11 to 15. 11 to 15. 11. Oh, goodness. 11 is there. So again, if you didn't say that was exactly at that and gave it a decimal point there, that's fine. We'd all be within 5% answer of each other. Okay. So what is that value? Let me just unzoom out. I can't handle this zoomed in anymore. So 11 to 15, that's about 11. I'm just going to say 11. It's pretty darn close. Maybe a 10.9, maybe 10.8, but it's somewhere between 11 all the way down to 10.7 in that arena, and down to 15. So that's one of those numbers divided by 4. Okay, I'm just going to, maybe your answer is going to be 10.9 divided by 4. So 2.7. So negative 2.7 meters per second west. Probably accepting anything from negative 2.8 to 2.6 or something like that. So you're now getting the understanding that when it's a curve, where's your values there? If it's a straight line, it's very predictable where you are. You know the equation of that line mathematically, so you know exactly where you are. When it's a curve, we don't know the equation of that line, so knowing our precision of where we are is an eyeball. Okay? What's the average velocity for the entire trip? Okay? What do you think that answer is? Yes? Yes. It is 0. Okay, because the displacement from beginning to end is 0. Which time frames is the object stopped? I would say almost none. Okay, almost none. Like, is it stopped here? Is it stopped there? Questionable. Is it stopped here? I would say yes. It is probably stopped right there because the slope of that curved line is 0. Okay, so at about maybe 9.5 for sure, But could you say 2 seconds and 4 seconds? Mathematically, no. In physics land, yes. Okay? And again, eyeballing it right about in the middle. Yes. It is. It is negative, negative 4.8 over 5, but in vector format, I just made it west, which is the opposite of the east. Yes, good. Good answer. Good, good, good. Which, number 4, during which time frames is the object moving west? Okay? West would be when the line is going down, and that would be from 2 to 4, and from about 9.5 to 15. Okay? And mathematically, is it moving west at 2? No. So we just leave it like this, leave the range, and which frames is it moving east? And that's 0 to 2, and then 4 to about 9.5. That's the other range. And number 6, between which time frames is the object traveling the fastest? Now, this is a good question. Traveling fastest, that means speed or velocity is really high. But we don't have the speed or velocity anywhere from this chart. We can get it though. How do you get the speed or velocity from a distance time graph? Well, speed is the slope of a dt graph. So when we're saying the slope is the largest, when the slope is the largest, then the velocity is the largest. So when I read this, and hopefully you see it now, between which time frames is the object traveling the fastest, is the same question as between which time frames is the slope of this graph the steepest. Where is it the steepest? Well, think about this is actually a ski hill. Where would you not want to ski? Where would you think that you'd be traveling the fastest if this was a ski hill? And I would say right about there. That slope there is the steepest. That's almost vertical. Almost. Okay, so where are you traveling the fastest? This would be just before 12. What is the total distance traveled during the entire trip? The distance traveled, observe, let's see if this is 8, and then this is 2 backwards, but that's still distance, so that's actually 10. So this is 8, and this is 2 more, okay? And then going from here to there, that's a rise of 2, 4, 6. So this section is 6 more. And then this is from 12 to 15. That's 12 more because it goes from 12 down to 0. Sorry, down to 0 at the time of 15. So it's distance. So it's not displacement. So we just add up all these numbers. It's 8 plus 2 plus 6 plus 12, and we get 28. What's the total displacement for the entire trip? 0. And now here is the question that I want to talk about quite a bit. What is the instantaneous velocity at 11 seconds? Fantastic question. What is the instantaneous velocity at 11 seconds? Given a dt graph, we're asked for what is the slope at 11 seconds. Okay, let's just erase all this. What is the slope at 11 seconds? At 11 seconds, it is right there. Okay, let's just zoom in. We want to know the slope. So if we placed a board along there, what would be the slope of that line? That's what we're kind of asking. If we touched that line in one spot, and that's the spot that we touch it right there, and we had a straight line, what would be the slope? Now, a conservative way of doing it is to, oh, that's awfully big, thick lines. Let's just make that line a little thinner. Right click, pen properties. Let's make it purple, but still thin. We want to drag in two lines there. See if I can drag it, and if it's going to let me not snap. That's close enough. And then I'm going to copy paste. Oh, why did it put it down below? Nice. Thanks, Microsoft. And I'm going to draw a steeper version of it that touches that one point. Maybe even a little bit steeper than that. So I'm rocking the board, this one purple board, from this location to this location, and you can see that the slope would probably be somewhere in between these two. So as a teacher, I'd find the slope of these two lines that I've just drawn, and the instantaneous would be somewhere in between them. This one is probably, let's just change the color there so we can refer to them as different colors. Let's make this green. No, let's make it red. How about that? The purple line is not steep enough, and the red line is too steep for that one dot. And if you think the purple line could be less, you can lower it down. But you're trying to eyeball it and try to draw a straight line that just touches at that one point. It's a very guess, visual, I'm going to draw a line. Now that you have a line, you extend it as far as possible. You extend it as far as possible to get the slope of it. Okay, so you start here. Okay, I started there, that's fine. And I get it as long as possible. Okay, I'm going to start somewhere in between. And I'm going to change the color of it just so that we're working with it. And I'll try to maybe make this one black. So that's the one I'm going to work with. I'm going to zoom out now to do my calculations. That black line is what the slope is that I'm looking for. So that goes from about that location all the way down to this location. That's exactly 15, we know that. And this one is maybe 9.4. Just guessing, it looks a little, maybe 9.5. Okay. I'll just do 9.4 just for the fun of it. And 15. So the run is 15 minus 9.4. And the rise, it goes from, this is a little easier, that number on the chart is 14. And this number is 1, 2, 3, 3.8 maybe. So that goes from the final 3.8, subtract the 14. So that's the rise. So it actually goes down over this time. So that's the change in the height over the change in the run. Let's get these numbers. 3.8 subtract 14, 10.2 negative. And let's do the run. 15 subtract 9.4, and that's 5.6. So 10.2 divided by 5.6, negative 1.8 meters per second. Okay, that's a good answer. If you came up with a different number, that's fine. Which numbers are applicable? Well, if I was a Mr. Nice Guy, I'd probably start a line here and find out the slope of that one. and that might be negative 1.6, and then I'd get a slope of this very steep one that I definitely know is not it, and that might be a slope of negative 2. And if you have a range of an answer anywhere in between them, good answer. Okay? You're trying to find the slope at that point. It's the instantaneous speed, not the average speed. An average speed is total distance over total time. This is the speed exactly at that point. It is the speed that you see on your speedometer as you're driving. Your speedometer tells you the speed at that point in time. Okay, painful, but let's move on. List the many differences between the time frames 4 to 6 and 10 to 12. Okay, and then there's another question there, number 10. But I'm just going to stop here because this one was the one I really wanted to say. Well, what's the differences? 4 to 6 and 10 to 12? From 4 to 6. So this is that part right there. I'll highlight it from 4 to 6 and 10 to 12. Okay, there's lots of differences there. One is a constant velocity, one is a changing velocity. One is moving forward, one is moving backward. One moves a further displacement. They do travel the same amount of time, so that one, each of them is 2 seconds. But the one moving backwards has a different distance. So there's some of the things that I would like you to think about. And let's just do the last question, then I'll let you go for a break. 11, what does the distance time graph look like when a car is slowing down and stopping at a red light, and then starting up again when the light turns green? Okay, so this is a distance time graph, position time graph. Notice at no point are you moving backwards, so at no point should it ever be going backwards. So you're moving forward and slowing down, and now you're at a red light, and then the light turns green, and you start moving forward. During the time where it's red, it's flat. Here you're probably going at a constant speed and then starting to brake and slow down. Here you're going from rest and changing and going faster and faster. So your speed is slowly changing and going up. And the slope is changing. And then probably for this last point here, it's a straight line because you're back up to the speed limit. So the slope of this line and the slope of this line probably the same. So this is an object moving forward, slowing down at rest, starting to go forward and at a constant speed. Thank you. Enjoy.